First one I just wanted to mention is that one, it was a while back. It was just that one with a couple, so it's really quite a while back. But why don't we just go over that real quick? This one. So what you want to do on this one is you're taking, now this is not an equilibrium problem. This is more like a resultant. We want to find the net effect of those couples on the supports. The forces are in the direction shown. What this is 221, I think it is. So what you would do, you just go to sum of the couples there and find what those are. So the sum of moments there would be, clockwise would be negative 7.70. Counterclockwise would be 13.3. So when you add those, you get the net, and I believe that's 5.6 Newton meters, okay? And then what you're doing, a couple, by definition, is force times distance with the force perpendicular to the distance. So all you have to do then is take the 5.6 Newton meters and divide it by the distance between the two, which you see there is 0.4 meters. So that's Newton meters. And you come up with 14 newtons. So what would happen there if you're looking not at the reactions, again, this is a resultant, at the effects on those forces, is you would have two 14 Newton forces like that. They're equal and opposite to get the couple. That's 221, I think. I handed that back a while back. All right. So that's that one. Now we're going to look at those zero force members, so let's have a look. Here we go. So all you need to do is to pull out the page out of your book. I believe it's page 18. And I just want you to mark the zero force members with a 0. And the goal here is to get where you can just identify these things by looking at them. They come up sometimes in trusses, so we want to find them. And essentially when you find them, you take them out of the truss. You don't want them in there any longer. So yeah, this is page 18. So all you're going to do is pull page 18 out of your book, put your name on it, and mark the zero forces with a 0. Okay.
All of them?
On all 5, yeah.
Okay.
So just find them is what I want you to do. All right, now here, there's 2 zeros right there. That's an unloaded corner, which is one place where the zeros are. If you go sum of fx and set that equal to 0, you'll see that that equals FBD. And then if you go sum of Fy and set that equal to 0, that will be FAB. And the free body diagram I'm working with rather is like so. All right. Now there might be a couple other zero force members in that truss, but I'll just point out to them. Well, I'll let you figure them out. I don't think DC is because there's just too much going on. You've got at joint D 1, 2, 3, 4 unknowns plus a load. Too much to analyze. At joint C 1, 2, 3, 4 plus a load. So that's too much. What you're looking for usually are
anytime there's a symmetrical triangle with something in the center of it, it's 0.
It's actually the things I'd be looking for on these would be unloaded corners, and that's what the example is right there. ABD is an unloaded corner. So that's a very good instance where you have zero force members. The other common situation is unloaded T's. So that's the other one. So those are the things you want to be looking for, and you can always prove it to yourself by drawing a free body diagram of one of the joints. And then do force equations to show that 0. So I would point out that BD, you would never be able to see that at joint D because there's just so much going on there that you would not be able to identify BD as a zero force at joint D. Okay, so you just find it at one joint or the other. There's probably a couple other zero forces in that one, I think. All right. Okay, this one here, what you could do is look at joint C, I think, and you could identify FC as 0. Now, as I just mentioned there, you're never going to see that if you look at joint F. There's, again, too much going on. But if you look at joint C, you should be able to go sum of Fy is 0, and that will be CF. Okay. You could also look at joint B and come to a similar conclusion about sum of Fy equals 0. Now you have an angle in there, you could call it theta. That would be sine of theta times whatever FBF is. But it doesn't matter what theta is. All theta does in this instance is function as a coefficient. So if that's the case, you're just gonna, it doesn't matter, right? If you've got some sine of some angle, that's just some number between 0 and 1. And you would multiply that by FBF. You would still conclude that FBF is 0. Okay. So
is all the weight on AF and EF?
Yeah, what's going on there when you transmit that load down through those members? The only two that can hold much of anything are AF and EF because they're supported. The other ones will start to sag a bit, but before they can sag much at all, AF and EF are going to pick that load up. That's what's going to happen. So there might be another 0 in there, I think. Okay. We're good with that. All right, we've got some others in here. All right, I think if you look at this joint right here, you can conclude from that that you've got a 0 right there. I better mark these. I better be consistent with how I'm marking them. I want you to put zeros on them. It's just easier for me to see them that way, okay? So right there, see, again, you might have an angle in there, call it theta or whatever you want. If you go sum of fx at that joint equals 0, what that's going to be is the sine of whatever that angle happens to be times FAB. Okay, so FAB then will be 0.
Could you go back to 302 for just a second?
Yeah, 302.
How come that B wouldn't be a 0 for member?
Well, I didn't say it wasn't. I said there's some more in here. I'm not picking them all out for you. I'm just showing you a few examples. So, yeah, I'm not getting them all for you. I want to take all your fun away.
303, wouldn't the compression from B to C create tension in A to B?
It wouldn't. Now, what's happening there? See, what's happening? We're I don't know how to say this, but we're not looking at what would happen so much at what doesn't happen. I mean, you have to look at these in a certain way, have a certain mindset. What's going on? B is an equilibrium, and so it has to be an X equilibrium. It has to be an equilibrium in the X direction. If that's the case, then there can't be any force in AB, because if there is, it will throw that joint out of X equilibrium.
Okay, it'd be moving.
Yeah, so, so now I understand you're saying wouldn't there be tension there because you're compressing BC. You think of a drag B a little bit, you get some tension. We're not really considering the deformation of the members so much. Okay, we're not there yet with our analysis of things. And the assumption then is that P1 is exactly in line with BC and that BC supports all of it. That's the assumption.
It's like perfectly perpendicular.
Right, yeah, perfectly vertical, whatever you want to call it. Yeah, it's perfectly in line. Okay, so the fact that this X direction is an equilibrium leads us to the conclusion that AB is 0. Okay, so there you go. This one, I'll let you look at this one. Now, I will mention that there might be some that don't have any zero force members. I just want you to look through this and kind of draw your best conclusions. So you can do whatever you want with that and mark any zeros you see with a 0. If you don't see any zeros, don't mark anything. That's okay. Okay. This one here, y'all see any zeros on this one to start? ED. Again, what you do to find zero force members is you look at joints. When I look at joint E, just 1, 2, 3, 4, and an extra force. I can't conclude anything by looking at joint. Yeah, right. Same thing with D. I got 4. And again, the equilibrium could happen in many different ways there.
How about BC?
Yeah, I think that's probably a 0 because we'll look at that. And then what we'll do is we'll do that and that. X and Y, we'll go sum of Fy, set it equal to 0. And whatever that angle is there, the sine of that times FBC will be the y component, and that's the only thing acting in the y direction. So from that, you can conclude that FBC is 0. Okay, so that's 0. Now, once a member is 0, you can take it out of the truss. It's like it's not even there. Okay, and if that's not even there, you can come up here, and remember, you can incline axes. And what you can do then is go sum of Fy prime is equal to 0. And what would that be?
About A to B?
Sorry,
B to D?
Yeah, B to D. See, we've got an angle in there. We're going to pick up a sine, whatever that angle is, phi. But then the only thing acting in the y prime direction is BD. Okay. So you can get that FBD is 0. Okay. And there might be some others in there. I think there are. I'll let you, again, go ahead and find them. But so I just wanted to just show you a couple of those, all right? So the key thing is you write an equilibrium equation for a joint to prove that one is 0. The common places where you find them are unloaded corners with 2 members and unloaded T's with 3 members. You could call this a special case of an unloaded T because there's a force, which you could think of as almost being like a member. There's the member, then the third one's here. So the third one, the one that is not in line with the other 2, is 0. You might think about it in that fashion. Okay. So I just want to get you some practice on this so you can identify the ones that are 0 and just eliminate them out of the truss. You know, that's often a early step when you're analyzing a truss. If you can find those zeros, you just take them out, and that makes the rest of your analysis easier. Okay. So we doing all right with that? So just like I say, just pull page 18 out, put your name on it, and mark the ones that are 0 with a 0. That's all I need. I don't need any of your logic. I don't need any write-ups or anything like that. Just a simple one, okay?